All right, so my computer here says it's the top of the hour, so I think we'll get started. Got a couple of items of housekeeping, so I'll give people a little time to filter in as well. Number one, thank you everyone for joining us today. We are covering kind of day one of our series on statistics with an ARM, and today we're kind of giving a nice overview of the topic at hand. Won't really dive into the software too much today. Have a PowerPoint presentation to discuss the statistics, kind of the theory of it, and we'll talk about in general using ARM with that. And then the next 3 sessions here in the series are going to be exclusively in the software, covering and showing the features that match up directly with what we talk about today. So that's the main flow here for everyone. And so the other item I want to point out is the chat. And I'll just put a message in here. This is a great place for questions. So kind of by default, everyone's muted here when we first join. Chat is a great way to pop in some questions. I'll have it kind of on my peripheral here as we're going through the presentation. So if it's something right in the middle of something we're discussing, we can bring it up, or also leave a little time at the end of the session as well to cover any questions people may have. So that chat works very well for that. And then finally, we are recording this session, and so we will post it later on today out on our website. So if you want to watch it again, or somebody who couldn't attend today and want to see what we covered, on our homepage, gdmdata.com, you'll find under the resources tab, we have a page for webinars. And that's where we post the announcement for this series here, as well as any others that we're having. And underneath that, you'll find the archives. And so we'll update and put the recordings from all of these sessions out there for viewing. So we had tremendous response for this webinar to the point where we actually had to turn off our registration. And so we took all the names of people who would want to have the recording sent to them even. So if you're live here, you got in and registered fast enough, and those watching the recording, thanks for tuning in a little bit later on as well. And we'll just keep updating those recordings. So if you do miss one of the sessions, you can always catch up before you catch us live in the next one as well. So, all right. Well, with that, we'll dive into the subject here. And again, that is ARM with the research statistics, kind of a nice broad overview. I'd really like to start by pointing out that I'm by no means a statistician. So today's look will definitely be an overview, but hopefully will provide a nice framework and kind of an understanding of what you would do in ARM, instead of some of the other looks. I think when we typically create tutorial content, it's pretty focused on here's what you do. And so we kind of wanted to take a little bit different approach, a different look at it, especially with a topic like statistics. It's just a little bit different beast, and so wanted to kind of give an overview of that world and just kind of explain how ARM fits in with it, instead of the other way around that some of our other webinars and training tend to lean towards. So, all right. If I can get my slides to advance here, okay. All right, so at a very, very high level, when we're looking at research, really the goal of it is to determine whether treatments of interest perform differently. And the choice of treatments, they can range from different products, different formulations, or even different rates of application. And really we want to know if those treatments can be distinguished from one another, whether it's their effectiveness, safety to the crop, or the cost. And sometimes you might even hope the opposite. You hope that the performance is indistinguishable, maybe if your product is cheaper than the other. So then we perform research, and so those research trials, then are performed to obtain observations of treatment performance. In ARM, we typically would call those assessments or ratings. But really the question boils down to, are the observed differences due to the treatments, or are they due to just random chance? And that's really where we use statistics, and specifically the analysis of variance is what we would do to kind of try to determine that and answer that question. However, you should not just immediately jump into the analysis after recording the data. So really I'm trying to split that up instead of just calling it data review. I think there's a couple of different phases in there. And so really data confirmation is really the next step that you need to do once you've gotten the data. You really need to kind of confirm the information that you've entered and recorded. That way you can try to catch any outliers or issues with the assessment before you actually go to the analysis. So, an outlier really would break all three assumptions of AOV. And we'll dive into exactly what those assumptions are a little bit later on, but an outlier would trigger skewness because it can cause your data to be non-normal. It can break the non-additivity requirement because outliers might not be distributed equally, and it can also mess with your heterogeneity of variance. And so again, we'll kind of dive into those later on, the specifics of them, but really an outlier can really mess with the analysis, and that's why we want to discover those, and the sooner the better, of course. So, how do we avoid problems and avoid that type of issue from happening? Really, you want to keep detailed records of the site and the assessment, and you want to confirm that data as soon as it's taken. And so, really it's, they're both kind of a little plug here for our TDCX add-in. Those are both kind of the core reasons for that tablet data collector feature to get your ARM software into the field. And so right when you're taking the data, you can use some of these tools in the software to catch any of those problems right while you're at the site, and you can make sure you're recording all of that information. And then one other thing you can do kind of before you set out for that assessment is to identify an acceptable range of values for that assessment before you even go out to take it. So then as you're recording the values, you have that range, and you would know, well, this doesn't make sense. This doesn't align with my expectations, and can kind of consider that and catch that as you're filling in the data. So this will kind of be the focus of day 2. Looking at our schedule for this series, really will be this data confirmation step and the different tools and features in ARM for this. I won't make it into a TDCX tutorial or an infomercial or anything like that. We'll stick to the ARM, but just kind of know that add-in is a way to get the software in the field. But whether you're doing it in the field or in the office, we'll kind of cover those features and how to utilize them in ARM, and that'll be tomorrow. So then kind of proceeding on to the next step really is the analysis of variance. That's kind of the tool that we'll use here in the analysis. And so, agriculture research is always subject to variation from a variety of sources. And so we perform an analysis of variance on the data. And your statistical variance, that really is a measure of how spread out the data is about its mean. So, sometimes it's called ANOVA or AOV, but the analysis of variance dissects the variability in the recorded assessments. There's controlled variability, which is your treatments and the blocking structure that you choose. And then there's experimental error, which is the uncontrolled error that you're observing. And so really we're considering if the observed differences are due to chance, then the variance between treatments must agree with the variance within treatments. And that's really really the core thought here that we're having within the analysis. So here I just wanted to take kind of example output here and kind of break it up to see how some of this information is formulated. And I just kind of use an example. We've got 5 treatments in a 4 replicate study, and the data here is on harvested yield. So starting with our first column here is the degrees of freedom. That one is a little tricky to define, but it's really the number of values in a final calculation that are free to vary. So specifically with variance that we're working with here, your degrees of freedom is n minus 1. So if you're looking at your treatment effect here, the degrees of freedom for your treatments would be 5 minus 1 or 4. And really the reason you take one off is that you have to calculate the mean in order to calculate your variance. And so that's kind of that one point of value there that is not free to vary, is that mean that you're calculating. So that's kind of how that n minus 1 comes into play. Then that next column is the sum of squares. And so that represents the amount of variation in the data. And again, we're splitting that up into each source that we're listing out in the AOV table. And we have, we're really splitting up by the blocks or the replicate between the treatments and then that experimental error. And then we'll total that up there at the bottom. Next column then is the mean square. And so that's the sum of squares divided by degrees of freedom. So really we're taking the total amount of variation that we have from that source and dividing it by the degree to which it can occur. And then we calculate that F ratio. So the second to last column there. And really that indicates the level of variation from that source compared to the random variation. So you see we take the mean square and divide. So for example, the replicate here, 101 is the mean square. We'll divide that by the mean square of the error to give us that F ratio. So the larger this ratio is, the more likely that the variance from the source is not due to just random chance. So to kind of quantify just how much so, how large would that F be to really matter to us, then we calculate a p-value. And so that's the probability that the observed differences in your treatment or your block, whichever source that we're looking at there, it's the probability that the observed differences in your means could have arisen by chance. So really you're looking for a low p-value would mean that we are confident that there are real differences among treatments. If you had a high p-value, like we see between blocks, 0.6, that indicates that there is no evidence of a real difference, among blocks here. So that could mean that there's simply, that there is no real difference to speak of, or that the differences that are there are too small for us to detect. So if we lost anyone by throwing numbers everywhere, kind of a summarization of all those numbers there, really the AOV analysis breaks apart the variance of observations into different sources. And then the end result, we get a p-value. It's kind of the end result there. And really think of the p-value as a probability. This is kind of the short way to think of that. And specifically here for AOV, the AOV p-value is the probability that no differences in treatments exist. So from our last page, we had the p was 0.04. That implies that we're 96% confident that there are significant differences between treatments. So that's great. In our example here, we're pretty confident that we have some differences, but we're not quite done yet. Typically, we now want to know, well, which observed differences between treatments are significant and which aren't. And so that's kind of where the AOV analysis kind of stops. It leaves us with the fact that, yes, we're pretty confident there are, or we're not confident at all that there are. But now if we are confident, well, what do we do about it? And that's where we utilize mean comparison tests. Sometimes these are known as multiple comparison tests or mean separation tests. But these really compare the treatment means to determine what differences are significant. So this is really going to run all those treatment means through to see which of these differences, because chances are they differ by varying amounts, what differences really are significant and what matter. So within ARM, there is a variety of mean comparison tests to choose from. And really the choice of which kind of depends on your situation and your research type. And these are kind of the most common ones. The LSD, Duncan's, SNK is short for student Newman-Kuehls, and then the Tukey's HSD. Kind of common question as well, which one do I pick? Which one should I use? And so kind of the first point to consider, certainly not a political discussion, but tests can be classified by how liberal or conservative they are. And really what we mean by that is if they're more likely to report a false positive, which would be your type 1 error, or to report a false negative, or your type 2 error. Another thing to consider is your penalty of failure for the study. So if your trial is being used for registration, then a more conservative test would be appropriate. You want to be certain of those results. But if you're just doing a screening trial where you're really just looking for potential, then you would maybe lean towards a more liberal test, because you're just looking for any chances, any potential there. So I do have a handout, and I'll make a note to include that link also in the email when we send out the recording. If you want to check that out, it's just kind of a 2-page, just kind of overviewing some statistics that we've used in previous trainings. And the big reason for it here relative to this discussion is it has a nice details about the different tests. So instead of kind of going through each test one by one and comparing them, would just kind of reference you to that document. It'd be the second page of that handout has, kind of goes in a little bit more detail on each of those 4 that we saw in the last slide and when to use them and when not to. All right, so that's kind of the exciting thing. It's certainly one question we get a lot in the support as well when it's reporting and analysis time is where are my letters? And so here we'll just kind of step through in general how a mean comparison tests work. The specifics, depending on which test you choose, the specifics will vary a little bit in how things are calculated, but we're really just going to kind of explain the basic concepts which fit for all of the tests. So the first thing that is done in that process is to calculate a test statistic. And so really this is going to be used to perform that comparison of means. So here in our example, we'll use the LSD, which was 5.49 for this data here that we used earlier. Then we take that statistic and we use it to compare the means. And so if 2 treatments do not differ by at least that LSD amount, then they are not considered significantly different. Then we assign letters such that such that means with no letter in common are significantly different. according to the test. So looking at our column of significant letters there, we can say that there is evidence that treatments 2 and treatments 5 differ because there is no letter in common, but there is no evidence of a difference between treatments 4 and 5. So they both have the letter A in 4 and 5, so they are not considered significantly different. And we did choose LSD here in this example, really just because it's the simplest one to explain, but just a little warning about that choice. So the LSD is really intended only for specific comparisons that you would choose before collecting the data. So if I had our number one main product that we're interested in, and we were going to compare it to a reference or a standard or something like that, you just really had one or two small handful of comparisons that you really were interested in, then go ahead and use that LSD value and zero in on those comparisons. But if you're using that LSD to make more than one comparison, kind of like in this case here with the trial, we're making comparisons against all treatment combinations, then the true significance level becomes much larger as the number of treatments increase. So really, as you're making more and more pairwise comparisons, really the total number of comparisons that you're making really increases. And so that ends up increasing your true significance level, and you're not really sitting at that. If you had a 5% significance level that you started with to calculate your LSD, if you're going to make 20 comparisons for a bunch of different treatments, suddenly it's not really a 5% anymore. Your chances of having a false positive would dramatically increase. So just a little warning about that test in particular. Again, that one is kind of the most liberal. We talked about before how liberal that is. So you kind of know that as you're using it anyway, is that it's more likely to have a false positive. As long as you're aware of that, then you can proceed when you know it's appropriate. So. All right, so that's really what we're doing in the analysis. There is kind of one big caveat that's been floating here in the background. We touched on a little bit earlier, but really it's that the AOV analysis has some requirements or some assumptions of the data that is being used. And so if the data don't meet those requirements, then we really can't rely on the results. So what are these assumptions? The first one here, homogeneity of variance. And really that means that the variance within the treatments are approximately equal. And so if you have a treatment that is much more variable or much less variable than the others, the ANOVA will not work. And so one way to kind of take a look at that would be if you look at a box whisker graph, the heights of those boxes create kind of a nice rough look at the amount of variance in each of the different treatments. Or you can also run a statistical test for homogeneity of variance. Both Levine's and Bartlett's are tests that are available in ARM for that. In general, Levine's is generally chosen, but Bartlett's is also available if you needed it. The next requirement is that the data is normally distributed. So if your data is not bell-shaped, then you can't use the same p-values in the analysis. So as Peter, our statistician, would say, it's just math. That's kind of how he tried to explain it to us, and that was those p-values we were calculating using that F ratio. Again, that's all assuming that your data is approximately normally distributed. And so none of those calculations will matter if your data isn't close enough to that type of distribution. And so the tests you can run to check for that, there's a few of them. So skewness and kurtosis are kind of a pair. They kind of test how peaked and how where the curve would be leaning, as well as the Shapiro-Wilks test is a general test for normality. Finally, the last two assumptions are independence of errors and additivity of treatment and block effects. These two are a little bit harder to test, not quite as cut and dried as the others, but generally they're not too big of an issue. Really, the biggest thing here is to not introduce bias in the assessment. So things like edge effects or subjective ratings, having a subjective rating can be influenced by some sort of source, whether it's the rater's fatigue, where you've been taking ratings for 5 hours straight, and so suddenly all the plots look about the same. So you started on a 1 to 10 scale, and your plots were between 3 and 9, and then by the time you're done, they're all 6s and 7s. Things like that. You just want to be careful with. Really, probably the number one thing you could look at kind of after the fact for something like that would be the assessment map. So that's kind of a heat map. They'll take your trial map and then display a heat map of your assessment values. So you can kind of get that spatial effect with the numbers that you've recorded, and you can catch various things for stuff like that. Really, a lot of those tests are, or I shouldn't say tests, those issues really are ahead of time. Planning, make sure that that you're doing a good job with your assessment and not introducing bias beforehand. Not much you can do, of course, after the fact. So really, a lot of these. This is kind of going into our third day here in our series with data review. Looking at the data and using some of these tests and such to take a look at the data in preparation for running it through the analysis of variance. So that's our third day really in this series, is focusing on how we can do run these tests and look at this type of information there in ARM. All right, so what happens then if we don't meet those assumptions with our data? There's a few things we can do. The first thing to try, there are data correction transformations that can be used. And these are really designed to correct the underlying distribution of the data without affecting the results. And so there's a log transform, a square root transform, and an arcsine. I think the full name of that one, arcsine square root percent transformation. And so really, you're running a transformation on your raw data, and you're going to transform each and every data point. So the goal being then that you're not changing your data, you're not massaging the data to fit something else, and change the results. But you're just changing the distribution of your data while maintaining the same results, because you're applying that calculation to all of your data values. And so, and some of that you can kind of predict there with the type of assessment that you're taking. So, the log transform is great for counts of things that occur in clusters. You end up with a log normal distribution for taking assessments like that. Your square root, that's for counts of things that occur at random or rarely. So if you're looking for the presence of kind of a disease and not expecting much pressure, or an insect presence, and you're going to have a whole bunch of zeros, 0, 0, 0, 5, 0, 0, 1, where most of the plots won't have that occurrence, but a few will. That ends up being a Poisson distribution. And then your arcsine, that is good for percentage data. Again, that ends up being kind of a binomial distribution, typically in a lot of your percentage data. And so again, all of those have various issues that won't fit those assumptions of AOV. Non-normality might be one of the biggest ones there, because really just the distribution of that data isn't going to match the normal distribution. So we're using these transformations then will have the transformed data now fit that normality and fit the homogeneity variance. And now we can use that data in the AOV analysis to find out our results. If those don't work or they're not an option or don't fix the problem, next thing you could try would be spatial models. And so spatial models really try to recover information about hidden variables across the field. So within ARM, two main types, there's a trend analysis and a nearest neighbor analysis. I think we have 3 different trend analysis and 4 of the nearest neighbor that are available in ARM. Really the big caveat here, typically you would only use those when your blocking design fails. You know, so if there was an unexpected gradient or the blocking didn't really take that gradient into account, or some other factor there that really causes the blocking design to fail and not work, then the spatial models can come in and kind of help correct some of that and get ready for that analysis. And then finally, kind of when all else fails, you can use non-parametric statistics. And really that just throws out AOV and all of its assumptions and say, let's try something different. And so instead, the non-parametric statistics really analyze the data by ranking the data values. And so really, you're looking, instead of using means and standard deviations in all of the analysis, you're looking at the ranks. And you can still perform a mean comparison test using the mean of those ranks, but now you don't have all of those assumptions that you must fit with the AOV. Instead, you have the non-parametric, totally sidesteps those. They are a little less powerful than the AOV test, just from the statistical power standpoint. And that's why, you know, really that AOV is option A. That's the first option, and typically what gets used in the analysis. But that doesn't mean non-parametric are no good, and certainly, especially in those ratings, as we talked about before, where if your assessment type is never going to be normally distributed, maybe that you would just know at the outset, I'm going to be using non-parametric statistics there. So that's kind of the last approach for those issues with the assumptions of AOV. And there's a good question here in the chat about those data correction transformations. So just stepping back here one moment on those data correction transformations, the question was, can we use those different transformations in the same trial? And so we'll see when we dive into ARM that all of these decisions, all of these actions that we're taking here on the screen can all be applied on a per assessment way. So you're looking at just each individual data column as you're filling in the data that you would apply one of these to. So yes, you can have all 3 different transformations in different assessments, just depending on your rating and how the data shaped out. So that's the nice way that ARM is structured, is that you're not making this decision across all of the data that you're going to analyze, but you're really looking at a single assessment. And of course, then you're performing many assessments across the trial. And so each of these, you're just denoting what action to take in the single column. And we'll see that again when we're kind of walking through this there in the data review. So that'll be day 3 again. We'll see exactly where we put that. But there's a field in the assessment header where we'll put that code, and that tells ARM when you're running the analysis, you should run this transformation or take this action. So that's a really great question. You're not making all of these decisions, really aren't on a whole trial-wide basis. You're looking at just a particular assessment at that point in time. There's what you're looking at. And that's really all I have for our overview here today. I guess I kind of had alluded to our 2 of the 3 other sessions, and the last session will be the reporting. So really focused on the AOV means table report is this main analysis, the AOV analysis that we talked about. That is how you perform that in ARM. And so we'll go through, specifically how to generate that. But most of the time will be spent on kind of common questions that we see with that. There's a lot of analysis choices and things like that, kind of related to a lot of this discussion here. And so that'll be our final session in this series, is talking about all of those common questions, how to format the report, some tips and tricks a bit too with that as well. So any other questions? If anyone has questions kind of about what we covered, hopefully there'll be a little bit more interaction. And once we dive into the software, today just wanted to kind of lay the groundwork, present an overview, and we'll just kind of take each of these chunks here of what we talked about today and apply them to the software, to what we do in each of the other days. So I have a question here about that classification from the most liberal to the most conservative. So let me back my slide up here a little bit. Actually, I'll go one farther back to see the list. So yeah, we talked about looking at those mean comparison tests. And there is a list of them in ARM, and you choose that in the report settings for when you're doing that AOV report. And so these 4 here on the screen are kind of the main ones that are used. There's a few other ones that have more narrow usage, but these are kind of the main 4. And so really they are ordered in ARM from most liberal to most conservative. And I probably would have to double check, but I think I probably put them in the same order here on the screen. So for sure, I know the LSD is the most liberal. I believe Duncan's is next, and then SNK. I could have those switched around. I'd have to double check. But again, you could see them in that list within ARM. And so that will tell you just kind of down the row how conservative they are. And then the Chuukey's HSD for sure is the last one. And that one would be the most conservative. So that one, again, to kind of recap on that, is that it's most likely to have a type 2 error, that we would have a false negative, that we would overlook a true difference and not actually, display that in the mean comparison. Whereas on the flip side of the coin would be that LSD, that is the most liberal. Now you are running you have a higher chance of having a false positive, that type 1 error. So it's kind of about balancing, and we alluded to it over here a little bit. It's a matter of balancing what's your objective. Do we really do you really need to be careful with those false positives? That what we're declaring here in the analysis needs to be definitely true. Something like a registration. Then you're going to want to run a little more conservative test. On the other side, if we're just screening, it's all about potential. We just need to know what products to take to the next level, to run next year and find out a little bit more about. Then liberal might be a better choice. Just to find any chances, and we'll find out next year, weed them out a little more and be a little more stringent on it. So that's 2 buckets at least to consider. That's really that penalty of failure, how you would choose that. And I think some cases it's a bit about your industry, or a little bit about your type of research. Well, here in this group, if we're entomology, we're all doing bugs, we typically use Duncan's. That in itself may or may not be true, but the choice of test might just kind of depend on the type of research too, if there's kind of a standard within that group. And I wouldn't know too many of those offhand, but certainly can check around with colleagues too to see if there is something like that. So thanks, Terry confirmed that, so thank you. So LSD and then Duncan and then SNK and then Tukey is the order for that. So the most liberal would be LSD and then Duncan's, SNK and Tukey's then would be on kind of that second half of more conservative, you would find. So thank you for confirming that. Another question about covering Abbott's and Henderson-Tilton transformations. I don't think we'll spend a lot of time on some of those. So like an Abbott and the Henderson-Tilton, those are not so much data correction transformations, but more about performing some sort of calculation on your data. So you know, the Abbott, you know, kind of a percent of control and kind of how you want to calculate that. So that one is a little bit outside of the realm specifically of you know, the data review portion, but I know that that's a very common question. So a good idea for maybe a future webinar for us to dig into the kind of those transformations and what to do with the data. You know, what other calculations should I do with my data? That might make a nice good webinar for the future, I think. Is stuff like that, because those are very common questions. There's a lot of, I know there's a lot of different flavors of Abbott's, and I think the Henderson-Tilton does something quite similar, but you know, subtly different in its calculation. So yeah, that would be a good one to cover separately. Probably not too much here, since it's not correcting the data and preparing it for review. So. Next question here, do you go into a trial knowing how you will analyze the data, or do the results dictate? And I think, and I'll admit here, I haven't done any research myself, and that might show probably already in some of the discussions and examples I give. But from the discussion I've been a part of in trainings and such, I think it kind of depends on your outlook, and maybe would depend on, that might be kind of an opinion question. I know there's some who feel that you should, you know, before you even begin the study or before you take the data, you should have an idea of how you would want to analyze it. And we had some of those examples where if it's percentage data, I'm probably going to need an ArcSine. If it's you know, those different types of ratings, you know, before you even take it, it's probably not going to be normally distributed. Or, you know, if it's going to be a percent of check, you know, that check is then going to be forced to 0 or forced to 100. So you know there's going to be no variability there. So I'm probably going to end up with homogeneity of variance problems in my data. So, you know, I think there's an argument for planning ahead of time, you know, and having an idea of some of these, I'm probably going to need it. But at the same time, you do need to look at the results, you know, and review them before you run them through the analysis. And you may find, even though, you know, here's my yield data, and I would expect there's a decent chance it should fit all the assumptions, but you need to take a look at it and make sure it does. And so, you know, maybe it's a little bit of both. I think either way, you definitely need to look at the data columns and review them to make sure that whether those results need to have a correction on them or not. But you could get a head start on them before you analyze, knowing the type of assessments that you're doing. And that might be a good question for a statistician if you have one available to see their idea on that as well. I'll admit my answer is a little bit more what I've heard. I can't say I have a specific reference to where there's proof of that or not, but I think a lot of that is this topic lends itself to a lot of that anyway. And then another question here about action codes or study rules. And so we'll definitely show those action codes probably in that data review, probably the third session especially, because that's really the action codes is where you go to put in those actions, those transformations that you would apply. So that's really where we'll go. I guess there's probably, off the top of my head, I can't think of any study rules that specifically lean towards the analysis. They're really not much. I think the choices with the analysis, I think vary so much that there's hasn't really been much requested as far as I need a rule to force the trialist to run it at 5% or whatever choice that study rule might want to lock down. Typically that isn't done too much, but yeah, we'll see the action codes quite a bit in our third day here. So great questions. I got one more here, on the LSD. So the LSD can show significant differences with a low number of treatments and non-significant with a large number of treatments. So I think kind of focusing on kind of the tail ending here, where I kind of warned about the LSD. I guess it's not so much that what it shows would differ. So here, we ran 5 treatments and we had a few differences. If this were to be 10 treatments long and kind of similar differences in data, your significance would still show this same separation. But really the key and kind of the warning I was giving is that those differences that are being displayed here, the more treatments that you have, the higher your significance level is becoming. And in that way, I mean that the greater risk you have for that type 1 error, that there's a false positive hidden within there. So, you consider here we have 5 treatments. We're really comparing, I'm not sure why it keeps advancing my slide here. We're really comparing treatment 1 to treatment 2, and then treatment 1 to 3, and then 1 to 4, and then 1 to 5, so on and so forth. So it really increases the number of comparisons you're running. And that LSD is so liberal and has such a high chance relative to some of those other tests of showing a difference that's not a true difference, that as you run more and more of those comparisons, it's much more likely that one of these differences that it's showing isn't actually a true difference. So for example, between 1 and 2, it is showing it's significantly different because they are far enough apart, but it's really just that risk there. With the LSD in particular, I think sometimes that one gets used a lot because you can have that one test statistic. And so in ARM, and we'll see it on the report options, you can actually, for your descriptive statistics, you can show the grand mean, you can show the standard deviation, you can show the LSD value. It's kind of a common value to show in the list just to describe that column and the analysis of it, but it's dangerous to use that for every single comparison. It's really was designed for, okay, I have 1 or 2 of the most important comparisons I want to look at. Here, product A and product B, we want to see how they work against each other and also to a reference. Well, I have all these other combinations I have in my study, and those are all great, but those are the main 3 comparisons I want to make. That's really what the LSD is designed for. So I just kind of wanted that warning to know that the more treatments you get, the higher you run that risk with the LSD. But that doesn't mean it's not a good test statistic to use in some cases. So, and thanks, Dan, for that tip there. That 12 degrees of freedom is good. So, yeah, here we had 5 times 4. Really good to have that degrees of freedom. I think we had that on a previous slide here. how many we ended up having. That was in our table here. So yeah, we had a total of 19 in the end, and so that gets us to that minimum. You for sure want 12 degrees of freedom in your study, and that really calls to the planning of the trial too, which we could almost fill another session of just talking about, taking your results and planning for next year as well, and designing your study. But that's a really nice quick baseline to check your degrees of freedom. That if you're under 12, you're not going to be able to really do anything from the statistical standpoint of being able to find those differences. So 12 degrees of freedom for the error. Sorry, yeah. Thank you for correcting me. It's the 12 degrees of freedom for the error is that minimum. Thanks for that. Yeah, not the 19, but the 12 there. So yeah, the 5 by 4 that I used just made it once you take out those treatments in the box. So thanks for correcting me on that one. For the error is that's the number you really want to look at for that rule of thumb at least. All right, well, thanks for the questions. Those are really great questions. I hope to kind of continue that dialogue. I think once we get into the software and we're going along, there usually seems to be more questions. It works great, especially then as we're going. I'll definitely stop if there's questions in between there to hit the different subjects as we're going along. But this was great to have some questions today and kind of lay the groundwork. So we kind of have that direction of, okay, this is why we're doing it in ARM, instead of just being in ARM and showing the features. I kind of wanted to have that overview. So if you have another question, feel free to send along. Otherwise, we can kind of wrap this up for today, and hopefully we'll see many of you again tomorrow. And then again the following week, and later on in a couple of hours probably it should be done building. We'll post the recording out to the website and send along that link. So thank you all for joining us today.